For years, AI coding assistants have focused on a single task, generating syntax. You type a prompt, and the model writes a function. But that workflow is breaking down. We are moving from simply generating code to establishing agentic repository design. Here is the problem. If an AI writes code faster than you can review it, you are no longer accelerating productivity. You are compounding systemic risk until the project collapses under its own weight. To tame that generation speed, you need an agentic coding environment. This is a workspace specifically configured to give the AI rigid boundaries, turning erratic behavior into predictable, testable outputs. Without these boundaries, an AI's speed is a liability. Once you engineer the context around it, that same speed becomes safe, scalable leverage. To build this environment, we divide the system into two distinct pillars: knowledge, what the AI remembers, and workers, how the AI executes. We translate these into a .claude directory. Under knowledge, go CLAUDE.md and skills. Under workers, go our main agent and subagents. Establishing this mental model up front is crucial. It ensures you never confuse a permanent project rule with a temporary, isolated task. Step 1 is establishing the AI's global memory. Run the initialization command in your terminal to generate a root claude.md file. This acts as the authoritative source for your high-level architecture and hard rules. Warning tone. But you must avoid the bloat trap. If you dump every project instruction into this single root file, the AI's context window fills with irrelevant data, severely degrading its adherence to your instructions. The solution is lazy loading. You take your detailed instructions and redistribute them into secondary claude.md files deep inside specific subdirectories, like your front-end or back-end folders. The AI will only load these instructions when it enters those specific folders. This geographical distribution ensures the AI's working memory remains lean and hyper-focused on the immediate domain. Every time the AI reads a file or executes a command, it consumes space in its context window. Think of this capacity as your token economy. As context fills up past 60, you structure your skill as a directory. The AI reads the main markdown file first and only conditionally loads the isolated scripts and example subfolders if the task actually requires them. To help the AI make that decision, you write YAML front matter inside the main skill file. This acts as a trigger mechanism, allowing the AI to autonomously discover the skill based on the current context. Progressive disclosure guarantees the AI only spends its context tokens on deep knowledge when the active task strictly requires it. If you ask your main AI agent to read dozens of files for a research task, it will instantly exhaust your primary context window. To protect your session, you use subagents. These are isolated, parallel AI instances spawned to perform heavy lifting in a separate environment before returning a clean summary. When you add the phrase "use subagents" to your prompt, the primary chat session cleanly pauses. The system safely isolates the execution by spinning up a new worker to read the files, returning only the final summary to your main context. Effectively utilizing subagents upgrades your role from a solo typist into an orchestrator managing a parallel engineering team. To connect the AI to external databases and environments safely, you use the Model Context Protocol. This enforces strict environmental boundaries around what the AI can see and do. But boundaries are not enough to prevent destructive actions. For that, you need hooks. A hook is a safety script that runs entirely outside the AI's predictive loop to enforce absolute rules. For instance, you can write a pre-tool use hook designed to intercept destructive terminal operations, such as a git commit or a post to your repository. When the AI attempts that action, the terminal halts. It sounds an alert and demands your human input before proceeding. Granting an AI autonomy is only a responsible engineering decision when it is bounded by absolute, non-negotiable human-in-the-loop safety constraints. Let's look at how this engineered system works in Harmony. You type a single complex prompt, and the orchestration loop begins. The AI lazy loads your local directory rules. It auto-discovers a required skill via the YAML front matter and delegates the raw data parsing to a parallel subagent to preserve your context. The AI then drafts the implementation. But before altering your codebase, the code commit is caught and verified by your deterministic safety hook. Transforming a repository into an engineered context minimizes hallucinations and protects your memory. This allows for a safe, parallel engineering workflow. To instantly deploy this architecture in your own projects, access the template link in the description below.